So it's an honor and frankly humbling to be here at Oxford and to be speaking to such a distinguished group. I'm going to be talking about a study that we are now in the second round of review on. So we're like fingers crossed, very hopeful that it'll be published soon. And this is a sneak preview. There are 25 co-authors on this study from about 13 different research institutions. Myself and some of the co-authors are from the Nature Conservancy. So unlike Stuart, I am unconstrained by much awareness about the challenge of actually developing technology, but so I sort of just have a pure love of technology, and I get totally excited about technologies that can solve climate change. One of the, and just some examples. So, we've heard a lot about, I think, different types of technologies for reducing emissions. I love solar panels. There's some powerful elegance about something with no moving parts that can transform our energy sector. I lust after the Tesla Model 3, which I really am trying to convince my wife to buy, but she hasn't really been convinced. And I'm also sobered by, I think what we've been hearing again and again is that even an ambitious scenario for ramping up technologies that will reduce emissions are unlikely to get us to carbon neutral by mid-century, which is where we need to get if we're going to achieve the targets of the Paris Agreement. So what does that mean? That means that we also need, in addition to behavioral change, and we also need negative emissions technology. And we just heard about carbon capture and storage. Here again, I'm thrilled by the prospect of investing in that technology. Clearly we have to do that. But also what's clear is that that's some time off in the future where it's going to become very cost competitive, where it can be scaled up globally. So, hypothetically, and this is again, I'm sort of unconstrained here, what is the perfect carbon and capture storage technology if we could snap our fingers and have it today? To me, if there was a machine, a device that used solar power to suck carbon out of the air and store it on site in a material that was actually useful, some kind of carbon fiber material, for example, that would be phenomenal. Unfortunately, that technology doesn't exist, unless, of course, we consider life itself. So the green stuff that's out there all around us has been evolving for billions of years to do exactly that. And so with that in mind, we ask the question, a simple question, how much can lands contribute by generating plant biomass, and that some portion of that which goes into the soils, how much can that contribute to mitigating climate change? So we brought together this group of co-authors to ask this question. Of course, there are others have done various analyses on this question. So part of this analysis was to synthesize the available studies out there that have looked at aspects of this, and then also to fill gaps to try to get as comprehensive an answer to this question as we thought we could. So the first challenge that we encountered is that we're not aware of a taxonomy that would actually describe all the different types of actions that can be taken to mitigate climate change through our lands. So we went about just making up a list of options. We started by thinking about 3 different types of actions. There's old-fashioned protection of intact ecosystems. We can restore native ecosystems, so we can expand the extent of native ecosystems. And then there's a huge variety of ways that we can improve practices on working lands. So these are lands that should remain working, but could store more carbon while producing the products we need from them. And we wanted to look at these three types of action across three major global biomes that are essentially the engine room of carbon storage and flux: forests, wetlands, and grasslands. And in the grasslands category, we include agriculture as an anthropogenic grassland. Okay, so with those types of actions and those three biomes, we came up with 20 what we're calling pathways. So these are simply just types of changes in land use, land management that can generate climate mitigation. First step, after we sort of developed this list of categories, was to look at what is the maximum biophysical potential. However, we didn't want to talk about a scenario where humans had to move to Mars. Not very interesting. So we constrained this maximum with basically three constraints in the way we actually defined the activities within each of these pathways. One is that we have to maintain and increase food production to feed a growing human population. We did include relatively ambitious scenarios about the ability to intensify production, but we didn't actually go to the most extreme scenarios. We just used a relatively ambitious scenarios about land use intensification. And again, this is for our maximum estimates. Second is that we need to maintain wood production. Wood is actually a lower, even badly harvested wood is a lower carbon footprint structural material than cement and steel, so we don't want to reduce wood production and then have it replaced by higher emissions materials. And third, we sort of a do no harm to biodiversity safeguard that we built into the sort of the assumptions we made in the design, the definition of each of these pathways. So for example, we limited the reforestation pathway so it can't be putting exotic trees into a native savanna ecosystem to generate carbon savings. That was not permitted in this set of pathways. Okay, so after generating these estimates, we then thought about what is a socially desirable level of implementation? Implementing at the maximum level has a variety of trade-offs and issues that are not necessarily, may or may not be socially desirable. So we looked at two price thresholds. So marginal abatement costs. The first one was $100 per ton of CO2 equivalents. Some of these pathways involve something other than CO2, particularly in the ag. And the second one was $10 per ton of CO2. So why do we look at $100? $100 has been estimated to be the price that society will need to pay to achieve Paris targets. There are a lot of estimates out there about what that sort of marginal cost will be, but we thought that was a reasonable estimate by reviewing the estimates that are out there. And that's, of course, to avoid a yet higher cost society would experience by not doing those actions. So we think of these $100 as sort of a cost-effective, maximum price for achieving less than 2-degree warming outcome. So we call that the 2-degree ambition level. And then we have the low cost of $10 I mentioned. And that's basically $10 is more or less what certain regions are already paying, price that's already been put on carbon. California, one example. Okay, so the next thing that we also included in this was getting pretty geeky, so I'm not going to spend time on this, but it's an assessment of uncertainty associated with the maximum estimates for each of those pathways. It was a challenging task because there's quite a range of information about uncertainty that's available for each of these pathways, but I won't go into detail on that. But the sort of take-home message is that those pathways with really big error bars are the ones that are particular priorities for additional research. I would just mention that all of this, the maximum and everything here is about additional action, okay? So this is beyond a 2030 baseline of management of each of these activities. So for example, for reforestation, we deducted the background anticipated, business as usual reforestation that would be occurring. We go beyond that. Finally, we just did sort of a relatively simplistic review of evidence for other co-benefits. Obviously, carbon is not the the only story in land use by far. So we just simply wanted to recognize a whole variety of other co-benefits that are associated with some of these pathways. And what sort of jumps out here is that the wetland pathways are characterized by consistently a wide range of co-benefits: air filtration, biodiversity habitat, water, flood buffering, water filtration, increased soil fertility. Forests, most of the forest pathways have elements of these, and then some of the agricultural pathways have all of these in sort of mixed bag there. Okay, so then finally coming to the question of how does this all, to the original question, how does this all add up? If you add up all of the 2-degree ambition levels, that was that sort of gray bar level for each pathway, it adds up to about 11 gigatons of CO2 mitigation per year. And by the way, that's sort of adding avoided emissions with enhanced sequestration, okay? Some pathways are avoided emissions, some pathways are enhanced sequestration. We add all those up, and we get to 11 gigatons. This is what it looks like if you can, yeah, I think it comes off here well. If you compare it to what would be needed to achieve this limited below 2-degree pathway as called for in the Paris Agreement, it's about 40% of the mitigation needed between now and 2030 could come from, sorry, I'm throwing another acronym in front of you. NCS is Natural Climate Solutions. That's just the whole package of all those pathways implemented at the 2-degree ambition level. About 40% of cost-effective emissions could come from these set of natural pathways between now and 2030. About 33, so about a third of the mitigation potential could come in the year 2030, and I say that because that's when we sort of calibrated our numbers most robustly to the year 2030. So about a third as of the year 2030, and between now and 2050, about 20%, so about a fifth. As you go out, of course, the need to dramatically mitigate fossil fuel emissions, is more dramatic, and the natural systems sort of saturate in the level at which they can provide provision. Now, these numbers are, the 11 gigatons is higher than prior studies. We didn't anticipate that. We were a little surprised by it because our estimates for individual pathways tended to be around the middle or lower than other studies that are out there, and in some cases we just use the other studies that are out there. And for some pathways we created new estimates when there were none. But the reason that our numbers are higher is simply because, as far as we know, nobody had actually added up that full spectrum of pathways. It's sort of that simple. It just hasn't been added up across that whole range of biomes and across that whole range of types of actions that could be taken. So, bottom line, I think to our surprise, natural climate solutions offer a bigger part of the cost-effective solution than we previously realized. And as sort of a personal reflection, I think that we've reached a point in human history when investing heavily in conservation and restoration and best practices in land use is no longer just a good idea talked about among environmentalists. I think it's a social imperative for everyone. Thanks.